I'll get started in the hope that I can actually finish at 5 o'clock and let everyone go home and have dinner, things like that. So I kind of stopped mid-sentence there because I hadn't been paying attention to the time. So I'm just going to pick up right again from thinking about this diagram and give you an example of the sort of thing that you can prove using this fact. So here's a theorem. So a connection on one of these weeds, Q, that I'd had written up there before, which looked like, what did it look like? It had 3 edges. Well, actually, sorry, it had arbitrarily many edges coming in. And then it had 2 little univalent guys hanging off the side. And then it continued in some possibly really complicated way a little while later. Okay? And now let's, on this graph, just give some names to things. Let's call that one P, that one Q. It's a different font, so it's okay. And this guy here in the middle, Z. And so all we need to say is a connection, blah, 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 exists only if dim P equals dim Q. That is, those bimodules have exactly the same dimension. Okay? Now, in particular, of course, before we talk about the theorem at all, the corollary is that so a subfactor with this principal graph exists only if dim P equals dim Q. Just because of this arrow here. If we had the subfactor, we'd get the connection. Okay? So, how do you prove a theorem like this? Well, essentially, it's just that these equations for the bi-invertibility of a connection are just some quadratic equations in some finite dimensional vector space. Okay? We've got this graph planar algebra space given by like this SSDD boundary, and we've got some element in the DSDS space, and we've prepared some quadratic equation by writing down these 2 equations, okay? And that's all we're doing to prove this theorem. We're showing there are no solutions to those quadratics unless there's some coincidence in the parameters, okay? It takes a while to do the proof, but the idea is just you analyze it some quadratics. Okay, so what do you get from this? Let me just show you how you. It turns out that knowing dim P equals dim Q is actually enough to do everything. So the corollary is that only if, so the subfactor only exists, it has the same index as this guy, where it finishes here with just a long string of edges, exactly the same number as was over here. And this is a completely trivial fact. This is just using the fact that the dimension of our favorite object x, the square root of the index, is an eigenvalue of this graph. And this constraint dim P, it's using something slightly stronger. If you think about the function, which is the dimension of each vertex, that is an eigenvector for the adjacency matrix of this graph. And this condition here, that dim P equals dim Q, basically lets you solve for the index of that graph. And it happens to be the same as the index of this graph. Okay? So that's an easy little calculation, just about eigenvectors on graphs. And then the next corollary is that in fact, only if it has exactly this principal graph, and roughly the idea here is if we had some more complicated principal graph like this, then there would be some planar algebra that was if you had some planar algebra with this complicated principal graph, you could argue that there was some subplanar algebra that just had this principal graph, but it would be at the same index because it's a subplanar algebra and index is preserved when you just take subspaces. But when you go up to a bigger graph, the norm has to strictly increase, so that's impossible. So that deserves more explanation. But anyway, you can just do a sort of a planar algebra kind of argument to see that the graph has to be exactly that. And then finally, you use only if it has this guy that actually turned up on the list in the theorem where those are chains of 3 edges. And this argument is finally just using the sort of cyclotomicity argument like we used for vines. Now there are 2 things that were varying at the same time, but you can run the same sort of number. Okay. And now we know that anything represented by this weed here actually had this identical principal graph. So what are we going to do to try and understand those? Well, we're going to analyze all of the possible connections on this particular finite principal graph. It turns out you're just solving a bunch of quadratic equations, and you can do this explicitly. There's an S1 worth of gauge equivalence classes. Of connections on this graph. And then you can explicitly compute the flat algebra. And what you see is that for all but 2 points, flat algebra is temporally Lieb, so it's not interesting. It's just temporally Lieb at the index of this guy. And so finally, you've got to understand, well, what planar algebra you get at those 2 points. Well, because a planar algebra with this graph would give us a connection, and it turns out we know 2 constructions, they're in the notes but I didn't talk about them, of principal graphs with exactly this principal graph, those 2 remaining connections are already occupied by things we know about, and there's nothing more to do. Okay? The analysis here was that there are at most 2 interesting connections, so at most 2 subfactors with this principal graph, and it turns out we can just construct them. Okay. So that's an example of how one particular of the 5 weeds we can deal with by this theory of connections and sort of some applied algebraic geometry solving some quadratic equations. So I'm going to skip forward a little bit and just not tell you about the other 3 weeds that were called B, C, and F in that theorem. But again, well, there are 2 papers about those that you can read. There's a few pages in the notes. But let me I want to just get on to the final part of this whole story. Everything we've been doing so far has been essentially ruling out possibilities, saying there cannot be a subfactor with these principal graphs, there cannot be a subfactor with these indices. But finally, at the end of the day, we've got some possibilities, and we want to know, are there really subfactors there? And we're faced with the problem that now we've got some principal graph, and we strongly suspect there really is a subfactor with that principal graph, and we've got to construct the thing. So the last part is this question of how you construct exotic examples. And the fact that I'm calling them exotic examples basically just means that we don't have good ways to construct them. And so really what I need to tell you at this point is sort of general purpose methods. If I show you the principal graph of the supposed principal graph of some subfactor, but there's nothing special about it, it's just some weird generic graph with nothing interesting about it, what can you do to construct a pivotal 2 category with that principal graph? Okay, so this is both a somewhat sad story because we're kind of just working with our bare hands, and there aren't beautiful constructions here. On the other hand, some really nice 2-dimensional topology comes into the story, and so I'm going to aim to finish with explaining how you end up having to think hard about 2-dimensional topology. in order to do this sort of construction. Okay, so there are sort of three approaches. So one is find, find 6J symbols satisfying the pentagon. So what do I mean here? Well, when you have the principal graph, that tells you some of the combinatorics of tensor product in your category. It tells you how to tensor on the right with a specific object X. Nearly always, and it tells you the list of simple objects. Nearly always, you can actually work out the entire tensor product multiplicities between all of the simple objects in the category solely from the principal graph, or up to some finite ambiguity. Now, if I tell you that I hope there exists some particular tensor category with a particular list of symbols and a particular tensor product multiplicities, there's some equations you can write down. Finitely many equations and finitely many variables, and they're at worst cubic, I guess, in degree. And solutions of those up to some gauge equivalence really correspond exactly to the tensor categories of those tensor multiplicities. So we can try that. Okay, we can find by unitary connections gamma, and if we can understand all of them on the principal graph we're after, we can then analyze their flat algebras in the hope of identifying that one of those flat algebras is what we're looking for, or maybe several of them are what we're looking for, and discarding the ones where the flat algebras are something else. Or C, we could look for our planar algebra that we're after with a given principal graph as a subalgebra of the necessary graph planar algebra. And then sort of after we've identified some subalgebra, show that it has the principal graph that we were after. Okay, so as far as I know, sort of these are sort of actually genuinely different approaches, and they all work in different cases. But for the sort of the regime we're looking in, this one works very badly, this one works some of the time, and this one works pretty well. So I just want to give a bit of an indication of how that actually goes. So let me just sort of briefly indicate sort of why this one is bad. Say you wanted to do this for the Aseda-Hagra principal graph. Is one of the possibilities that came out of our combinatorial classification. I got the computer to help me here, and it told me that there are 465,976 equations in 72,208 variables, and a 356-dimensional gauge group acting on those solutions, and the problem is to identify the orbits under that gauge group of those solutions. So it's kind of bad. That's well beyond the sort of the limits of applied algebraic geometry. I'm going to talk only for the rest of this talk about this approach, but it turns out that Aseda-Hagra was actually first constructed by Aseda and Hagra by using approach B, not approach C. So it already gets dramatically better. Okay, but let's go on to C. So to look in the GPA, we need to look for particular elements. So what I'm going to show you now is just staring at a principal graph, how you can realize that there must be elements of the associated planar algebra satisfying certain equations, and then you can go and look for elements in the graph planar algebra satisfying those equations. So for, say, actually for any of these guys, for H group, Zeta H group, or extended H group, or actually anything where the graph starts just with a triple point, before maybe continuing on in some more complicated way. The magic numbers, remember those? These were this decomposition into annular multiplicities. The magic numbers are 1. The empty diagram always generates an annular module in the graph planar algebra, sorry, in the planar algebra. The stuff that it generates is just the temporally Lieb subalgebra. And then it turns out there's a whole lot of zeros there. And then there's some new guy after n-1 zeros. Some new generator of an annular module. And so what you can prove is that so thus there exists some element S in Pn plus satisfying some nice equations. It's uncappable. Anywhere you stick a cap on it's 0. It's a rotational eigenvalue in the sense that if you do this 2-click rotation, you get just some multiple of itself. And well, okay, I'll talk about that lambda in just a moment. And moreover, it turns out that in this situation, when the graph just starts with a triple point, this space Pn plus, it's got a whole lot of temporally Lieb stuff, and you can actually see that it's just one dimension worth of stuff beyond a temporally Lieb. So this Pn plus exactly consists of temporally Lieb direct sum the span of this new element S. And as soon as you know that, you know that if you square S, by square I mean look at this planar composition of the two, that's some other element in that same space, so it's got to be a linear combination of stuff that we saw before. And it turns out you can actually read off the coefficients in terms of parameters that are just that you can read off directly from the graph. So this thing here is that Jones-Wenzel idempotent that I mentioned this morning that didn't actually define. Some particular element of the temporally Lieb algebra. So the point is that we can prove that just knowing this amount about the graph, there must be some element satisfying all of these equations. And via some work of Jones and Snyder, you can actually often read off this omega as well, which root of unity you're looking at, purely from the graph. Now, it turns out that this is already extremely powerful. Equations 1 and 2 are just linear equations. And so we can solve those very, very easily. So we solve 1 and 2 in the graph planar algebra. So we've got this huge space of loops of length 2n on this graph, then we cut down to some linear subspace given by all of those equations. The dimension of the solutions is actually in general pretty small. It's the numbers were 4, 16, and 21 for these 3 exciting cases of H group, Zeta H group, extended H group. Then try to solve 3, which of course is quadratic, in that space. Okay, this is obviously much more reasonable than the problem that we had all the way back up here. I mean, essentially what this analysis is doing is telling you, well, in some sense you can think of it as this analysis is telling you that amongst all these equations there are some that are particularly easy to solve. It's giving you a clue about how to organize that ridiculous computation. Okay, so it turns out you can do this, although for a Zeta H group and extended H group, it's actually very difficult and involves well, some fancy tricks in order to be able to solve it. You're already out of the range where sort of normal polynomial solvers are struggling but it's doable. And then what you find is, so we now have a candidate. Well, okay, so we try to solve this, and what we find is we end up with finitely many solutions to this quadratics. And in fact, the finitely many is not that important. There are some automorphisms relating them. So you might imagine that it's just a unique solution at this point. So now we have a candidate for the planar algebra. Let's just take, how do I write this? Or write it like this, sitting inside the graph planar algebra. So what I mean here is just the planar algebra generated by the element S, which is an element of the planar algebra. So everything that you can get by taking planar compositions of this element S, their span in all of these vector spaces for the graph planar algebra. Okay? That thing is certainly a planar algebra, because we just defined it as the planar closure of this element S. And it's the smallest thing containing this S, so we might hope it's the thing that we're after. What do we need to do in order to check that this candidate answer that we've got here really is a planar algebra with the desired principal graph? Well, we've got some planar algebra. We basically just need to check that it satisfies all the axioms for a subfactor planar algebra, and then identify that it has the right principal graph. It turns out that identifying the principal graph is actually not that hard, the difficult bits are actually just checking that the planar algebra is the right sort of planar algebra. So what do we need to check? Well, this thing that we just obtained, G sub S, is automatically unitary and spherical merely because the graph planar algebra is unitary. Well, you asked right back at the beginning of the day if you could even define spherical when you weren't evaluable. The graph planar algebra doesn't have one-dimensional zero-box spaces, but there's an analog of spherical that you can define, and it turns out that all subalgebras just inherit those properties. So those things you just get because the graph planar algebra has those things. It has the right index. Because the loop value is just determined by the graph planar algebra, and all subalgebras have that loop value too. But it is not obvious that the zero-box space is one-dimensional. In particular, remember the zero-box space of the graph planar algebra has a basis consisting of vertices of the graph. The n-box space is loops of length 2n, so the zero-box space is just vertices. The graph planar algebra itself has quite large zero-box spaces, and if things went wrong here, we would really expect that the planar algebra generated by S was just going to be the entire graph planar algebra. And so that's the main challenge. So to show that this equals 1, we need to identify further relations satisfied by this element S, which suffice to evaluate arbitrary closed diagrams built out of S. Okay, so a priori, this thing is just all planar diagrams built out of some number of S's glommed together. And this is sort of where the planar topology comes in. So the idea is to use the jellyfish algorithm. It's kind of neat. In fact, it was invented in the paper where we constructed this extended Hagerup guy, which had been a curiosity for a while. And it turns out now we're understanding the jellyfish algorithm is actually extremely useful. And there are lots and lots of variations of it that let you prove all sorts of theorems about planar algebras. But this was sort of the first instance. Okay, so first I need to show you what a jellyfish relation is. Let me do it over here. Okay. So these candidate generators in the graph planar algebra, called S up above, for Hager or for extended Hager. So for Hager, the S is in P4, and for extended Hager, S is in P8. Satisfy some relations. And they're a little bit crazy, but show you what they look like. There's some crazy coefficient here, which I'll use the convention of calling squiggle. Actually, maybe let me make life a little bit easier by instead of drawing lots of strands there, just drawing a single strand with a label next to it to tell you, you should think of this as cabling. This is 2n plus 2 strings next to each other. Now, what's that F in the box there? Again, it's this Jones-Wenzel idempotent that I talked about before, which is some linear combination of all the temporally Lie diagrams. Okay, so there's some relation of this form, and then an even crazier one. Two strings over above the S. Different squiggle there. Okay. Okay. So identifying these relations is actually, well, it's a bit of work, but it's not really the interesting part. The interesting part is what you do with these relations. So I've given you these relations where there are these crazy Jones-Wenzel idempotents on the bottom, because that makes life easier. But what does a Jones-Wenzel idempotent look like? Well, F superscript n, always looks like the temporally Lie diagram, which just consists of vertical strings, okay, plus some linear combination of all the other temporally Lie diagrams which have cups and caps in them, okay? So what I'm going to do here is I'm going to take all of these Jones-Wenzel idempotents that you see everywhere and expand them out like this as the vertical strings term and all the other junk. And I'm going to move all the other junk over to the right-hand side of these equations. So that means that I just get to erase the boxes here, because I'm just keeping the terms where all of the strings went straight through the Jones-Wenzel idempotent. And I get to erase the boxes here. But now I need to add a bunch more terms, plus, and I'll just describe them as lower order terms. And why are they lower order terms? Well, if you took any of these terms where there was a cup or a cap in one of those Jones-Wenzels, that cup and cap would have kind of collided with one of the S's in some way. And remember, there were these relations that said that caps hitting S's gave 0. There were uncappable things. And, or alternatively, it might do things like hit an S there. But then we know about how S acts underneath rotations because it was a rotational eigenvalue. And so somehow all of the terms that involve cups or caps involve strictly fewer S's in them, and so are somehow simpler than the ones that have joined. Okay, so these are what we call jellyfish relations. What on earth are we going to do with these relations? Well, I claim that these relations suffice to evaluate an arbitrary closed diagram. And so I'm going to show you how to do that by by giving you the jellyfish algorithm for simplifying a closed diagram. And actually, let me, I'm just going to keep using this board because I want to have these inside. So I'll just erase this out. So the idea is that we're going to think that our S's here, the generators, are our jellyfish, and the strings that you see hanging down below them are all of their tentacles hanging down here, and we're just going to try and float all the jellyfish up to the surface, okay? Using these relations. Here there's an S and there's something above it we can float through. Here there's two things and we can float through those. There's actually because I've been omitting all of the shadings, it turns out this relation, floating through a single strand, only works in one of the two shadings. And so we really do need this one as well, which enables us to skip two strings at once if we happen to be in the wrong shading. Okay. So let's say it. So theorem is that that's one-dimensional. The proof is float all the jellyfish to the surface. So let me give you an illustration of how this goes. Let's imagine I have some closed network built out of S's. These strings might represent many strings connecting in parallel. And I pick some region that I declare to be the surface. It's the water up here. Now, these jellyfish here are actually already near the surface, but this guy is down deep in the ocean. Okay? So we start floating him this way, and he passes some number of strands along the way. Okay? So we repeatedly use these relations. So this jellyfish maybe splits apart into many little jellyfish as he goes, but the point is that the total distance between those S's and the surface is strictly decreasing. So we can eventually bring this into the form of a diagram like this, where there are maybe significantly more S's than there were before. 5 is bigger than 4, I guess. And then hanging down below these guys is just a whole lot of jellyfish tentacles, some element of temporality sitting down below. Okay? So that's sort of the first step. And I think a really curious and fun thing about this jellyfish algorithm is that there have been lots of instances in the past of sort of diagrammatic evaluation algorithms, like some local rules that let you manipulate planar diagrams. For example, all of the famous knot invariants kind of work along these lines. But this is a really curious evaluation algorithm because it doesn't, it makes things more complicated as it goes along at an intermediate step. Basically, every instance we had previously of evaluation algorithms for planar diagrams had some complexity function which they could reduce as they went along. You can cook up some complexity function that you're reducing, like sum over 2 to the distance to the surface of all jellyfish, something crazy like that. But you can't concoct a local complexity function that you can compute as a sort of sum over different parts of the diagram. So something kind of curious is going on here that didn't happen before. Okay, we're not done yet. This is not a multiple of the empty diagram. So we need just a little combinatorial lemma. Let's just rewrite this picture here. This is all just template leaves. It's just a whole lot of strings. So I want you to think of this picture. Well, we're going to forget about the surface again. But we're going to draw all of our S's as the vertices of some polygon. And now all of the spaghetti here just means that we have some collection of diagonals drawn into that polygon. Okay? I'm just, you see what I'm doing? Going from here to here. And the little lemma is that polygons with diagonals have corners. That is, there's always some vertex of the polygon where there are no diagonals incident at that corner. Okay? That's a pretty easy thing to prove. And so let's look at that particular S there. Okay? That particular S there has in total 2n strings coming out of it. And because there are no diagonals coming in, at least one of its two neighbors is connected by at least n strings. Okay? So let's suppose it's that edge there that's greater than or equal to n. So let's zoom in and look at that. Well, that's a pair of s's connected by at least n strings. Hopefully this is still on the previous page. Partly erased. Here we've got exactly this situation. A pair of s's connected by at least half their strings. It doesn't really matter if they're connected more, that just corresponds to closing off this diagram. But we can rewrite that pair of s's in terms of strictly fewer s's. And notice that if you do this, to this pair of s's here, it reduces the total number of s's, but it also leaves the entire closed diagram in jellyfish form with all of the s's adjacent to the surface. So we don't need to rerun this first step, which would bump up the complexity again. At this point, we can just run downhill, always reducing the number of s's by collapsing some adjacent pair. And so that eventually leads you to some multiple of the empty diagram. Okay. Now, I didn't really carefully say exactly what was going on there, but the essence was that we identified some subalgebra of the graph planar algebra that we hoped was the right thing. There were a number of things we needed to check, and I just promised you that nearly all of them were easy to check. This was the hard one. But as soon as we knew this theorem, this subalgebra of the graph planar algebra we identified really is some subfactor planar algebra with the right principal graph, realizing that possibility coming out of the big classification theorem, and so plugging one more little hole in the classification. And it turns out that you could run analogous arguments of various complexities for all the different cases in the classification and get to exactly where you want it to be. I guess that's the end. I'll declare my theorem proved. I even finished 1 minute early.